Hello everyone, this is Singh 𝐂𝐴 and today we are deep diving into one of the Discord engineering blog which talks about how it supercharges network disk for extremely low latency. तो इसमें हम deep dive करने वाले हैं. We will be discussing all the things related to how it does it and what kind of problems Discord was facing earlier. So if we before moving forward, if you haven't subscribed to the channel MsDeep Singh, consider subscribing. We keep on making content around system design, distributed systems and cloud. So you will learn a lot of things in your career journey as per your interest in system design and distributed systems. So if we talk about the engineering at Discord, right, we already have created 3 videos as of now around messaging architecture, around how it stores billions of messages and how it indexes those messages, around those kind of things, and how it handles burst when there are millions of messages being pushed to the customers, the notification handling system. So in this video specifically we are talking about how Discord optimize their storage space so that it can allow the queries, the read queries to be faster specifically. So there are 4 million messages through platform by millions of people per day. So if we talk about per day metrics, there are a lot of messages being processed. Now if there are a lot of these messages are processed, they are stored somewhere, right? So we need some kind of operations, or we need there are certain applications which want to query that data. How you can do it efficiently? So as of now, Discord uses SkylaDB. Earlier they used to use Cassandra. There is a separate block on this, how they moved to Cassandra, how they moved from Cassandra to SkylaDB, what kind of problems they faced in Cassandra. So we might cover that in another video, but in this video specifically, let's talk around this is the base target. Let's assume that SkylaDB is one of the database which they use, and it is the source of their truth. For indexing specifically, they use Elasticsearch. Okay, so for storage and as a source of truth, that the data is always stored there and the data will be always present there. For those kind of use cases, SkylaDB is used. Now these SkylaDB clusters are deployed somewhere, right? This is your, let's say, SkylaDB code. This is your SkylaDB code. It will be deployed somewhere, right? So you need some kind of underlying storage system where this code can be actually deployed. You are not using any cloud technology. Let's say in case of AWS, we have DynamoDB. So in case of, if we have DynamoDB, we don't have to worry about the underlying storage system. Okay, so let's say we are using this text. Okay, so let's say we are using Amazon DynamoDB. Now if you are using Amazon DynamoDB, we only have the capability to specify the partition key and sort key, and like if they're required, that you can create indexes, LSIs, or local secondary indexes or global secondary indexes on top of it, but you don't have the capability, or you don't have the visibility on how it is actually stored on the disk specifically. Okay, so the SkylaDB code, okay, so you use the SkylaDB to code to deploy on some kind of disks. Now what kind of disk you should use, this discussion is mostly focused around that. Okay, so let's take a simple example that you want to deploy some kind of database. So the most preferred choice for it can be any database. It can be your MySQL database. You just downloaded the database and then you want to deploy it somewhere, and you want some kind of underlying structure to make that persistent storage. So in AWS specifically, you can use EBS. Okay, you can use EFS. EFS is your network shared file system. EBS is more preferred one because it is relatively faster, and for certain these kind of use cases where you want to deploy your own database or such, so EBS is a preferred choice. EBS is your persistence data store. So this article specifically talks about 2 data stores. One is instant store and one is persistent store. So these are in specifically to Google Cloud. Discord uses Google Cloud as their cloud platform. If we talk about the similar technology in case of AWS, instant store is same as instant store, and this persistent store is your EBS, elastic block storage. Now there are a lot of capabilities which are associated to it. What the basic difference which is in these 2 kind of storage is, first is it's a temporary storage. okay, and the second one is persistent, or and it is a permanent storage. As the name suggests, it's a permanent storage. So in case, let's say, the disk has failed, or the disk has failed, then the EBS maintains some kind of replica so that it can come back. But in case of instant storage, in case of disk failures, you will lose the data. Also, there can be scenarios that this disk is attached to one EC2 machine. So if this EC2 machine stops or hibernates or updates or anything, any operation or any update happens on the EC2 machine, this data, the instant store which is attached to it, will be lost. Okay, so in these kind of scenarios, EBS is a preferred choice if you can't lose the data. Because if there is a data, if there is a requirement that you cannot lose data, you want a perfect redundancy on the data, then you will not be able to use the temporary storage. As the name suggests, you can't use it. But there is another point of consideration around this. There is another point of consideration around this, which is this instant storage directly attached to the EC2 machine, but the EBS is somewhere available on the network. Okay, it's present definitely in the same availability zone. Let's say this is your AWS region, and you this have this your AZ1 and this is your AZ2. Okay, so and here are your EC2 machines and here are your disk. So they are definitely attached across the network, but the instant store is more closely connected to the EC2 machine, so it has relatively faster IO operation. So it is relatively faster operation. If we talk about speed, it is relatively faster. So these things we will have to take in consideration while we take the decision around how, or like which kind of device, which kind of internal disk we should use for deploying our database. Now let's this was one basic context which I want to set before moving forward. Now let's discuss around what kind of problems the Discord were facing and how they want to optimize it further. Okay, now the first discussion is around that if the operations are not so huge, if the operations or the number of operations are not so huge, then normal queries, like all the queries will perform in an optimal way, and it's not that noticeable. But if the number of queries increase to a huge extent, in that kind of scenario, we will be able to observe that there is some lag while you are trying to process the queries. Okay, so in these kind of scenarios, you will have to wait for an outstanding disk operation to complete before it issue another. So how it works is, let's take this simple example. Let me see if I have already drawn it here. I didn't. So how it works is, let's take this simple example. What is the simple example? So let's say these are your applications. Okay, these are your applications which access this database layer. We have deployed our SkyLerDB. This is your SkyLerDB application. Okay, and there are a lot of disks which are attached to it. Okay, so as you get the queries, you forward these queries to the disk to retrieve some data. Let's say you are trying to read some kind of data, so you will forward those queries to disk. Now there is a certain threshold, right, till which these queries can be supported. There is a certain threshold till which the queries can be supported. If we are breaching the threshold, let's say there are 100 total requests which can be served at a time. If there are more than 100 requests, let's say there are 110 requests, so these 10 requests will be queued in between. Okay, let's say this is your queue. Your 10 requests will be queued in between, and as you process this request from this 100 queue block, then these requests will be forwarded to disk. So if there is a huge burst, this queue will have a lot of messages. Okay, and it will keep on waiting, and definitely there can be scenarios that the queue size has become so huge that you are not able to process this application request, in the given time possible, and the request will time out. So this is the scenario we are talking about when we say if there are a lot of operations, definitely the problems appear when we work at scale. So we have to somehow solve it, right? If the scale is not so huge, then definitely there are less chances that you will observe some kind of problems. But if there are like a lot of operations happening, or a lot of traffic is trying to be solved, then definitely the issues can occur, and that's what we saw in case of Discord. So what we want to do is, we already discussed this part, that what happens is that the queue of operations and it explodes to a limit that it keep on it will become a problem of timeout, and eventually will not be able to resolve the queries, or we will not be able to return the response for the queries which we get. Okay, so these things, let's discuss around how and we another thing which we discussed already was how these queries can be solved. So discussed Discord and most of its hardware on Google Cloud, and they provide access to local SSDs, NVMe based instant storage which do have incredibly fast latency profile. We already discussed this, that Google Cloud uses this instant storage, which we mean by instant storage is that it can be used for storing that temporary data. Okay, so but in case of critical data, if there is a critical data, then definitely instant storage is not a good choice, because there can always be scenarios. Instant storage definitely has a capability that you can replicate the data as well, but there can always be scenarios that you are not able to do in some, let's say, a very 1% chance from the 100%, of 0.1% of the 100% chance. But this is a critical data, you can't lose it. This is a critical data, you can't lose it. So in these kind of scenarios, you will have to use some kind of persistent storage, so that the data is replicated on the go, and you don't have to wait to do it manually at your end. So instant storage will not be a preferred choice in that kind of scenario. Okay, instant storage will not be a preferred scenario in the case of critical data storage requirement. Okay, so let's move forward on this. So the another main instant storage for GCP is called persistent disk. This is the comparable to EBS, elastic block storage, which we discussed. There are certain other mechanisms visible as well for persistent storage. Persistent basically means that you can keep on keep the data stored till the time you want it, till the time you don't delete it. So one is EBS in case of AWS, one is EFS, and then finally there is object storage, which is S3. So we are specifically talking about EBS and then instant storage here. Okay, the block storage specifically, we are using block storage. We can definitely use other type of storage as well, but if we talk about database operations to be served faster, then EBS and instant storage will be preferred choice to go about it. Okay, so let's move further. So the disk can be attached details from servers on the time can be resized. These are the benefits of the EBS you get, that you can increase the size of the EBS, or you can decrease the size of EBS dynamically without observing any kind of downtimes. So this is definitely a benefit when you are using EBS, but the downside is that these disks are just directly to server but are connected from somewhat nearby location, probably same building. This we already discussed, that instant storage provides faster IO operations. Why it provides faster IO operations? Because they are attached directly, but the EBS volumes are attached over the network. So consider scenario where this is your EC2 machine and this is your instant store. Okay, so they are, let's say, attached directly via a 1 meter cable, and your, let's say, these your EBS stores which are located somewhere around let's say 10-meter distance away. So definitely these things come in picture, or like will reflect some kind of latency driven operations when we are talking about scale. This might not be a much latency driven operation when we talk about little scale, but it will definitely be effective. It will definitely be effective when we talk about high scale. Now let's quickly discuss around we already discussed this, right? And this is the example of example graph here, which actually depicts this latency. So this is your blue graph is your persistent disk latency, which is EBS specifically, and this is your local disk. So if you see the latency, right, it is jumping till 2 milliseconds, but if you see for the local disk, it's half a millisecond. It is less than half a millisecond. So definitely there is a latency issue if we are talking about high scale. Now local SSDs have other concerns as well as with traditional hard. Downside is hardware issue with one of this means this we already discussed. Okay, is what happens when hard is most attached. Critical issues, the disk data gone forever. Okay, this we already discussed. In case of EBS, you will have a scenario where you can create snapshot easily. It is a persistent storage. That functionality will not be available in case of your instant storage. Okay, so this we already discussed. Now let's discuss around the problem, which problem we are facing here. So in perfect world, we'll power our database with the disk combined with best properties. So if we discuss about our use cases, right, we need kind of mixed properties from both of these. We need a kind of a mixed properties from all these of both of these solutions. One is EBS. EBS provides snapshot functionality, backup functionality, then instant storage faster. Instant storage is faster. So we want to combine these capabilities. So let's discuss the problem first and then try to solve it, how you can achieve this combination of two storage systems. Okay, so in a perfect world, we'll power our databases with a disk that combine the best properties of persistent disk and local SSDs. Unfortunately, definitely there is no such disk available. You will have to determine your use case, you will have to determine your business use case, that this is the requirement at hand and this is the disk solution I am choosing. But if you are looking for a combined solution, then we will have to reiterate over the requirements, how you can make the best out it or make best out of it. So asking for low latency directly attached disk removes the abstraction that gives persistence disk their amazing functionality. So definitely if you are going with the one, then you will lose the benefits which are offered by the other. But we see, we don't require we don't need all the functionalities which are offered by the persistent storage. We need some of them, we need just some of them. For example, one is the dynamic sizes. So what we mean by dynamic sizing is, dynamic sizing means you have configured the EBS volume with 100 GB. Now on the go you can make it 150 GB, on the go you can make it 90 GB. Okay, so this is the functionality, this is the one feature which is being provided by the EBS or the persistent storage. But can we survive without this feature? Can we survive without this feature? We can survive without this feature via proper planning of hardware and storage capacity planning. That this is the, let's say 100,000 dB I require. So in this case, if I'm able to determine this specifically, this number specifically somehow, then I don't need this kind of capability. So this is all this is what we are talking about. What if we didn't need all this flexibility? For instance, write latency isn't critical for our workloads, it's the read latency that has biggest impact on application performance. Okay, so when we are talking about this is the one scenario. Another scenario which we already discussed around the resizing. Okay, and another one is that we are specifically interested in read latency. Okay, so instant storage will offer good latency for both read and write. But we are only specifically interested in read. We are specifically interested in read. We are not specifically focused, or we can live without the properties, or we can live without the functionality being provided for the write operation. So these are the two things which you can make benefit out of it. Okay, so let's discuss around the clear requirements, what we gather from what we gather from both these two storage systems. So first is Discord definitely want to stay with the Google Cloud. So what we mean by this is, they are not looking for a solution which is let's say deploying their infrastructure on their own premise or something like that. They are focused on leveraging the GCP disk offering only, considering the operational management and all those things. So this is the current situation, that Discord is using the disk offering which are offered by GCP. GCP is Google Cloud product basically. Continue using point-in-time snapshotting for data, because this is again a critical requirement, that we need a data redundancy support. So we need data to be backed up continuously. In case of AWS, let's say this is your EBS volume. So let's say you are continuously backing this data to S3, which is object storage. Got it? Then further, the third requirement is prioritize low latency disk reads over all other disk metrics. So this is our important disk metric which we are prioritizing, which is disk reads. We are specifically trying to optimize the disk reads. Write latency is one which we can survive with, but read latency is the one which we want to be prioritized and should be optimized to a best use case possible, best number possible. Do not sacrifice existing database uptime guarantees. We want our system to be available, and it's like if we are prioritizing this discrete latency, if we are prioritizing this discrete latency, then we don't want the solution which you developed, the solution which you developed is definitely definitely reducing the latency, but it is hampering the availability of application. So this should not happen. Okay, so these are the four requirements we are looking at when we are trying to choose a disk offering which is provided by the GCP. Okay, so the different GCP disk types meet these requirements in different ways. Okay, there is no single disk. If there is a single disk which can meet all these requirements, then we are good to go. Okay, there is no further requirement of this block, but this is not being offered by Google Cloud. So we need to figure out some kind of mixed solution which can meet these kind of which we can meet these four requirements. Okay, so the different GCP disks which meet these requirements in different ways. It would all too convenient if we could combine both disk types into one super disk. Okay, so since Google Cloud don't have an offering which could meet all these requirements, then we need the disk to be combined into each other somehow, that you are constructing a super disk. super disk कैसे कि आपने मानो एक तो instant storage लिया, you took instant storage and then to EBS volume, you combine them, this is your super disk, and then you have combined functionality of both instant storage and then EBS. So this is what we are talking about, a super disk. Okay, so you are gaining the both the functionalities of instant storage as well as you are getting the functionality of persistent storage. So for local storage you are getting the low latency while still writing to persistent disk, which provides the capability of snapshotting redundancy via replication. Okay, so let's see how you can create this super disk. So what we have described with our requirement was essential write through cache. What we mean by write through cache is you are actually writing through a cache solution first. Okay, and then you are trying to write to a persistent storage. Okay, so what we want was we had a requirement for read. We have a requirement for read. So what we are trying to do is we are trying to store the data at both the locations. Okay, so this is your, let's say, Skylar DB cluster deployed, and these are the disk solutions. These are the disk solutions which are present. So what you will do, you will store the data at both these locations. Okay, you will store the data to instant storage as well as you will store the data at persistent storage. Since this is works on the philosophy of write through cache, you will first store the data with instant store and then persistent store. Okay, so this persistent store is responsible for permanent storage of disk, permanent storage of data. Okay, and this instant store is responsible for serving the read queries. So this way, this will act as your caching solution and this will act as your persistent storage, and this is for reads and this is for writes. So this is the first approach that came to our mind, how you can actually create the super disk leveraging both instant storage and persistent storage from Google Cloud offerings. Now in case of Ubuntu, so this code uses Ubuntu on database server. So we were fortunate to find that Linux kernel was able to cache data on disk level with variety of ways. You can actually create caching solutions on the disk with DM cache, LVM cache, and B cache. So specific to these, I will share some links with you, but I haven't personally used them as such. I have basically read the descriptions how they work, but I haven't personally used them how they actually work. So definitely I need more deep dive if I want to explain them to you. We can definitely do it if that's required, but for this video specifically, let's skip that. So Discord figured out that there are disk caching solutions already available in case of Ubuntu, which we can leverage in case of Linux, which we can leverage. One is DM cache, then we have LVM cache, and when we have B cache. But so what you can do, you can use this instant storage as a caching solution via this disk storage solutions. So but there are some problems which are associated with these caching solutions. What are these problems? So the biggest problem is how the failures are handled. If there are any failures happening. Now let's discuss around. So let's use this pen. How this is looking, it's looking nice. Okay, so how you will handle the failures. So reading a bad sector from cache caused entire read operation to fail. Now what we mean by bad sector, let me quickly give you a overview. Is it written, it's somewhere? No, it's not written. Okay, so what do I mean by bad sector is it's permanently damaged this sector. So let's say this is your disk. Okay, this is your instance storage and this is your block storage. So let's say these are your blocks created, chunks created where you actually store the data. Now this is your sector 1 S1, this is your S2, this is your S3, this is your S4, this is something like that. Okay, and this is your, let's say, S25. Now in case some sector gets corrupted, in case some sector gets corrupted, let's say this sector got corrupted, this sector got corrupted. So in these kind of scenarios, the read operation will fail. In these kind of scenarios, the read operation will fail, and eventually we will not be able to serve our requests. Okay, so local SSDs, a thin layer on top of NVMe SSD hardware, suffer from bad sectors like any other physical disk. Definitely the failures can happen. So if there is an issue with bad sector, these bad sectors can be fixed by overwriting the sector on cache with data from storage layer. This is the solution which can be used to overcome this, but this was too complex to implement. And how you can actually do it, you will fetch the data from your persistent storage and then update it, but this was too complex to implement, and the solutions which were evaluated by Discord were not that straightforward. Okay, they were either complex or they required some extra kind of configurations which they skipped at that time, because that might be taking much time, and they saw some other alternatives that can be used. Okay, so without the cache fiction back sectors, they will be exposed to a calling application and the database will shut down for data safety reasons. And this was the error actually. Okay, this was the error actually, that shutting down communication due to IO errors until operator intervention, disk error. So this is your bad sector error. And Discord has this configuration that if something's around this happens, then there might be some safety reasons associated to it. An application should not be accessing those bad sectors, so it will eventually fail. Got it? Now let's discuss around how you can solve it. And what were the other alternatives that were explored by Discord. So with our requirements updated to include survive bad sectors, so this is additional requirement. We had already had 4 requirements earlier. We had these earlier 4 requirements, these requirements. Now we have another requirement which is surviving the bad sectors. If there are any bad sectors which are present on the disk, we should be able to handle those sectors, and our request basically should not fail with these kind of error. Okay, moving forward, so we have our 5th requirement, which is survive bad sectors on a local SSD. So Discord investigated, and there is one Linux kernel system MD, which could be helpful here. What we mean by MD is multiple device driver. This is basically a software device driver which can be used to manage the physical disk on your physical disks which are present as hardware, and how you can actually manage them via the software. So this Linux kernel system MD, a device driver, is can be used to solve that use case, and it uses RAID, redundant array of independent disk, how it arranges those physical devices or physical disks to store the data and then retrieve the data. So basically MD is responsible. You can think of it as a mechanism. To read and store the data on physical disk. Okay, there are a lot of physical disk present, and this MD will provide the different mechanisms, and these mechanisms are referred as RAID. Okay, RAID, these mechanisms are referred as RAID, and there are different levels which are available with RAID, how you want to actually store it. So let's quickly give it a read from here, and then I will explain you how there are different RAID levels and how they differ from each other. Okay, so MD allows Linux to create software RAID arrays, turning multiple disks into a one array, virtual disk. So there are a lot of disks available. Let's say these are those lot of disks available, and via software you can represent them as a one. So it is single large virtual disk which you have present there. Okay, so you got the basic gist about the MD or like the Linux kernel system which is offered to manage the hardware disk. Now let's quickly get an overview about RAID that will be helpful to understand these further paragraphs. Okay, so let's quickly focus on the different RAID levels which are being offered. Okay, so when I say RAID level, what I mean is by RAID level, what I mean is that what kind of support we need on the read and write, and how do we need any kind of redundancy support as well. Okay, manner in which devices are arranged into an array and how the data chunks will be stored in there. So first one is RAID 0. So this is your stripped array, zero redundancy. So this should definitely be not used for production use cases. Now don't say that this is used by SkylarDB in production. When I say production, SkylarDB, we specifically discussed that we are trying to use this for instant storage, and it is anyway instant store in it is anyway a storage solution which is not redundant enough. It is a temporary block storage, so definitely we can use it there. So don't think in that way, just try to understand the use case. When I say we should not use it for production, what I mean is if we have a use case, the data should be durable, then this is not a preferred solution. Now how the storage works is you will understand this, what this stripped array means by this description. So how the data is stored is the driver assigns first chunk of array to first device. So when I say device, there are multiple disks available, right? There are multiple device available disks, right? So the first available chunk will be stored there. Okay, so let's say these are your two disks. Okay, so let's say this is your first chunk. So first chunk will be stored here A, then this is your second chunk B, then there your third chunk C, this is your D. So this is how your actual storage works in case of RAID 0. Okay, and this collection of chunks forms a strip. And this is what we mean by stripped array. Okay, so this is what how the data is stored in RAID 0. Now let's quickly discuss around RAID 1. It is a mirrored set. When I say mirrored set, the data will be replicated. Okay, the data will be replicated among the disks. So changes are returned to all the devices in parallel, and each device in RAID 1 array contains exactly same data. So let's say take this same example. Okay, let's take this same example. So let's quickly erase this. Okay, so if you are storing A here, then A will be stored here as well. Then you are storing B, then storing B is here as well. C. Okay, so the data is actually mirrored in case of RAID 1. Okay, so it's providing a good redundancy here. Changes are returned to all the devices in parallel, and each device in RAID 1 array contains exactly same data. Since you are replicating the data across the devices, then definitely the data will be same. Now data can be read from any device. Since we have a data available on each and every device, then data can be read from anywhere. Let's discuss around read balancing. Now driver distributes the read request across all devices to maximum performance. Since there are a lot of devices available from which the data can be read, if the driver is able to come up with an algorithm, a certain kind of algorithm, then that can definitely be used to improve the performance. Okay, so let's say there are a lot of devices available and this is your driver. So to figure out from which device the data has to be, I don't want to send all the operations to this specifically to read certain data. I can divide the data and I can divide the request among these multiple devices so that it can be proper balanced. This is what we call as read balancing. Now individual devices in RAID 1 can be marked as write mostly. What we mean by this write mostly is they are skipped from read balancing and only be read if there is no other option. Okay, so let's try to quickly understand this specifically. This operation or this functionality is being used by Discord. What we mean by this is, so let's say you have these bunch of devices. Okay, you have this bunch of devices. Let's say you have 3 devices. Now these one device is marked as write mostly. Okay, this is your driver. Now all the read request will be served from here only. Okay, all the read request will be served from here only, and in case that the data is, let's say, corrupted or like any other scenario that we are not able to serve the responses from these two, then only the request will be routed here. So this is the functional, you can think of it as a flag that this device, specifically this D3, is specifically marked as write, especially marked to write mostly flag, and this will be most only focused around writes. Okay, so in this case the read balancing or the division, or you can say distribution of read request will not be forwarded to this write mostly. Now okay, so now let's move to our blog of Discord. You got the basic description about how you got the basic description about what are raid 0, what are raid 1. There are other raids available, which is raid 5, then raid 10. Okay, there are other rates available, but we are not discussing in context of this engineering blog. You can definitely just Google them and you will get the idea around them. In this blog specifically, we are only concerned about RAID 0 and RAID 1, around how Discord use them. Okay, so a simple mirrored RAID 1 array between local SSD and persistent storage would not solve our problem. Reads would still hit the persistence for about half of the operations. So uh, what this mean is that in this architecture, if we had something like, if we had let's say something like, let's say this is your RAID 1. Okay, and this is your instant storage IS, and this is your persistent storage. Okay, and this is your Scylla app. Okay, so SCY. Okay, Skylab, this is your RAID 1. So in this case, if you have such kind of architecture, this is the problem which is described here. What is the problem? Read would still hit the persistent for about half of the all operations. Why? Because it will do the read balancing. That some of the request will be routed here and some of the request will be routed here. But what we want is, we want to serve all the read request from the instant storage. We don't want the read request to be served from this persistent storage, and that's where signs are write mostly flag. We talked about write mostly flag. So if we configure this persistent storage as write mostly, then in that scenario all the read request will be served by instant storage. So that's what we are talking about. Okay, now this is the one point which is clear. Now let's move further. Okay, so additional features not present, one of which is write mostly. This we already discussed. So indeed, individual devices in RAID 1 can be marked as write mostly. These devices are excluded from normal read balancing and will only be read from when there is no other option. This we already discussed. Slow link is your persistent disk. Okay, so we have marked our persistent storage as write mostly, and we want to serve our read request from the instant storage only to get the maximum out, because we know that the read latency will be minimum in case of instant storage and it will be more in case of persistent store. So we want to serve all the read request. From there. Okay, moving further, since devices connected over a slow link just happens to be perfect, this we already discussed. A RAID 1 array containing a local SSD and a set to a write mostly would meet all our requirements. Okay, so this we discussed, that you have configured the write mostly flag to the persistent storage, and this should solve the problem. Now there is one final problem which can occur. So local SSDs in GCP are exactly 375 GB in size. So in this architecture which we discussed, what is our architecture? Our architecture is, this is your Scylla DB application, then we have RAID 1, and then we have divided the data into divided the request into two, which, and the persistent storage is marked as write mostly. Okay, now there is another problem which can occur. Okay, this instant storage size, the instant storage size in Google Cloud can be maximum of 375 GB. There should be some similar kind of limitation in AWS as well. I have to check on the number, but just Google search and you would get the number. But no, the basic concept is that there is a hard limit. Okay, we had this functionality in case of EBS, that you can directly dynamically increase the size of EBS volume or the disk space, but you can't do it in case of the instant storage. So there is a certain limit, but this 375 GB cannot solve our use case, right? We need more storage space to actually store our data, right? We need terabytes of space. Per database instance for certain applications. So this is nowhere near enough space. We could attach multiple local SSDs to a server, but we needed a way to turn a bunch of smaller disk into a larger disk. Okay, so the solution, the one simple solution could be that this is your server and you can attach multiple instance storage. Okay, but then you will have to manage the mapping that in which actually instance storage the data is stored. Okay, but we don't want that, right? We don't want that. We need some kind of management layer in between, which can do this management, and that's where the helpful is RAID 0. Okay, that's where helpful is RAID 0. In RAID 0 we talked that the RAID 0, when you pass on the chunks will be stored on the devices serially or sequentially, that you have stored A here, stored B here, stored C here. In this fashion you are storing the chunks. So you can you introduce RAID 0 in between? There is definitely one problem in RAID 0, which is that if a disk is lost, the entire array fails and all data is lost. So we will need definitely some kind of mechanism to solve it. It is offered by RAID as well. RAID 5 and RAID 6, which maintain the parity and allow the loss of at least one disk at the cost of performance penalties. Okay, it is offered by RAID as well, but it will be coming with additional cost of performance. Okay, it will be coming with additional cost of performance, and we don't want that. Our major requirement is performance, read performance. So we want to optimize that. So to come up with I will quickly read through this so that you don't skip it. So this is great for maintaining uptime. Just remove the failed disk and replace it with a fresh one. But in case of GCP, we don't have such this is not in our hand, right? So if we talk about GCP cloud, in case of RAID 5 or RAID 6, we mentioned that in case of particular device failing, what you can do, you can go and then go and then replace it. But in case of GCP, we are not managing those disks, right? GCP manages those. We are not in the ownership of those things. So GCP has to do that. So to avoid all this confusion and to make it a simple solution in a performant way possible, because our performance is a key factor, right? So RAID 0 is finalized to turn multiple local SSD into a one low latency virtual disk. So this is the finalized solution, that what you can do, this is your finalized solution. This is your application. This is your let's say SkylarDB. Okay, so it will hit the request to RAID 1. This is your driver. It will hit the request to RAID 1. RAID 1 will forward the request to both, because RAID 1 is RAID 1 replicates the data. It replicates the data to all the devices. Okay, so this is your device 1, this is your device 2. So it will store the data to RAID 0. It will store the data to persistent store as well. The persistent storage is marked as write mostly, and this is your and the read balancing will happen only in this specifically. Okay, so this RAID 0 has multiple disk instant storage attached, and they will be represented as a single virtual disk, large virtual disk, where the data is stored. Okay, so this is the final solution. This is the final solution which is being deployed by the Discord server to handle the scale which we are talking about. This is the diagram which I have also drawn it here. So this is the final solution which is deployed with RAID 0 on top of local SSDs and RAID 1 between the persistent disk and RAID 0. We could configure the database with disk drive that would offer low latency reads. This was one of our requirements, while still allowing us to benefit from the best properties of persistent disk. And what are those benefits? Those benefits are, we want point-in-time recovery. We want to maintain proper backups. So persistent storage signs there. We want a durable solution. So persistent storage signs there. So this is how the final solution was designed. There is just one confusion which I got from the blog. So if one disk is corrupted in RAID 0, entire array is lost. Okay, this is what happens when a RAID 0, any device in the RAID 0 is corrupted, and it can definitely happen, right? So how Discord reconstruct data in RAID 0 again as new hardware is restored? There is no answer, but is specifically mentioned in this blog. Definitely as mentioned here, they might publish a new blog how it is handled, which is mentioned at the end of this engineering blog. So if the new blog comes, then definitely we can discuss it further, but there should be some kind of backfill algorithm in place. There could be some backfill mechanism in place in case in case this goes down, in case this data is lost, how this data is backfilled from persistent storage, because in here we don't have any backups, in here we don't have any management of backups. So if this data is lost, how it can come back, because we definitely want our read request to be served from here. Okay, if the data is lost, we don't want our read request being forwarded here, right? We want our read request to be served from here only. So we will definitely need some kind of backfill mechanism so that the data can be re-persistent again here. And it is not described in this blog, so definitely I can not talk about the actual solution which is in place. But yeah, so this was the solution means developed. And if we talk about the performance, this was the improvement which we got on super disk and persistent disk. This is the super disk and this is the persistent. So if you see, the latency in case of super disk is highly optimized, or like relatively very less as compared to the persistent storage which we had earlier. Got it? So this is all which we will be discussing today in this blog. We will meet again with new videos around system design and distributed systems. If you enjoyed this video, like this video and share it with your friends, and don't forget to subscribe the channel. We will keep on making content around system design and distributed systems, and you will learn a lot of things. We will meet again. Till then, stay safe. Tata. Bye bye.